But right now, I want to present to you Jonas Schabak, which is the co-founder of Visual Meta. Welcome him.
So I will drill down from a basically top to bottom, there we go, perspective. So I will quickly talk about what the product is, what we do, what we accomplish, what the value add is for the user, and then I will talk about a little bit about the architecture and what the actual machine learning algorithms are that we employ in order to accomplish our task. And in the end, we'll have hopefully some time for Q&A. So at 12, we should be done. And then, yeah, I'm happy to answer the questions. So this is me. I've been co-founding Visual Meta, the company that I'm talking about 8 years ago. And I'm running it as a CTO. So I'm still very technically involved. In my free time, I'm part of the SB21 group, which is a business angel group. And I'm, well, trying to invest and support startups that are looking for funding and support, especially in the tech sphere. So if you're interested, let me know, right? Before that, I've been working at Rocket Internet as a software developer, and before that, I was trying to study computer science. Well, I finished that, but I was trying to study machine learning with Mikio Braun, by the way, back in the day. So that was fun, and I learned a lot back in those days. And I'll show you what we do today. So the main product of Visual Meta is LadenZeile, which is a German comparison site for fashion and furniture in particular. We build the largest e-commerce fashion and furniture catalog in Germany. That means we're aggregating all the different products that come from Zalando, from eBay, from Amazon, you name it, and we put them in one unified, huge catalog for you to search through it. The benefit is that you save time, so despite of going through all the different online shops because you're looking for a particular pair of shoes, so you only need to go to LadenZeile in order to find the product you love, because you're basically simultaneously searching through 8,000 shops at a time. So we aggregate all this data in order to provide a user, for example, with the complete set of all red women's perms of the German market. So this is basically depicted here. So, and in order to get an overview for the user, right? I mean, he has to search through about 130 million products. We basically have 3 ways of letting our users search. The first one is a visual similarity search. You may have found a product that you really like, and it's too expensive. That's actually the usual case. So then you would like to know, okay, what are the products that look very similar but are not as expensive? Well, that's where this visual similarity search comes in. So you would pick a candidate, product, and the system finds for you visually similar products. Oh, that's interesting. There's supposed to be a slide. Lele? Well, anyways, the second type is actually keyword-based. So you could always search for EANs, for product numbers, for different ways of basically describing your product by a name. And the third one is based on tags. There we go. It's actually loading or something. No drilling, but problems with the slides. So basically what we do is, maybe I'll just progress. So what we build in the back is a huge ontology of the entire shopping world. So we basically have to come up with all the different categories from the fashion and furniture world. And by that, we create the taxonomy of all the different categories and subcategories and filters and potential attributes and properties that all the products may have in the back. And we organize that in a hierarchical order of attributes. So we're trying to describe the entire shopping world by means of tags. So we skip over here. And basically, the tags here are describing the products. So what's important to understand is that at the time when we load the data, we do not know anything about it. So at the time when we load, at the time, this is basically the architecture, at the time when we load the data from Amazon, Zalando, eBay, you name it, we don't get it in any structured or meaningful way. It's totally chaos. It's semantically chaotic, it's unstructured, it may be a CSV file, but we have no clue whether the particular product that we're looking at in one of these huge feeds is actually a shoe or a furniture item or a particular pair of, I don't know, drilling equipment. So in order to figure this out, we need to apply some magic here, and this is where basically our machine learning framework comes in. In particular, as I said earlier, we have in the back a huge ontology of tags that we assign to all the individual products. And by adding more and more tags over time to these items, we get more and more meaningful data because we describe the items more and more accurately, right? In this particular case, we have two women's shoes, right? So that's why they share the women's tag here. In this case, it's a pump, not a sports shoe like this one, and this one is red, obviously. So we assign red, pumps, and women and shoe to this one, as well as to this one, women's and shoe, because they're both a shoe, obviously, and sports and Nike. And we do that in a fully autonomous and unsupervised way, although the learning is basically the training of the machine learning in the back is supervised. All right, so we talked about the ontology. This is manually crafted by experts who are very well educated in the field of women's shoes and stuff. So I'm not, but there are people who are very, very well equipped with that. So what we do then is basically we train classifiers for each individual tag in order to come up with a binary decision on whether a particular tag is supposed to be assigned or not. Because at some point you need to decide for each tag that we have in our taxonomy whether it belongs and should be assigned to that particular item or not. And we do that by exploiting the hierarchy of our taxonomy. So that means we start with the broadest tag at the very top and then work our way through all the way to the bottom. So in the first case, we would decide, is a particular item a shoe or not? Right? It could be a furniture item, a DIY item, it could be, I don't know, it could be a bench, whatever. So let's look at this example. So in this case, we would say, yes, it's a shoe, and we would assign the tag shoe. That's great, because at the time we know it's a shoe, we can discard a huge part of our research space. We don't have to decide anymore what sort of furniture it would be, or what sort of DIY power tool it could be, because it's definitely going to be a shoe, which is a fashion item, right? That's great, because we reduce the dimension of our problem space. So on the second layer then, we have other tags, which are basically coming from our taxonomy. And then we have to decide, okay, is it a pump or a sneaker? We don't know. It's mutually exclusive because it can only be a pump or a sneaker, right? We don't know that. So what we do then is basically we have trained classifiers for each tag and let them decide basically in a majority voting way. So what we then do is, okay, in this case, the classifier 2 would say, hey, I'm very confident this particular pair of information that I see here is definitely going to be a sneaker. All right, so it's definitely not going to be a pump. And this is how it goes all the way down, right? On classifier 4, it would decide it would be a chock. There would be more sibling tags on the same level deciding against it, and that's how it works in our system. So what sort of machine learning algorithms do we actually employ? There's various, to be fair, and we came up with very simple ones. The first one is just looking up whether particular keywords occur in the description. Very simple, but very robust. Then we combine them basically in the majority voting way with support vector machines, which is basically a combined simple keyword-based classifier and a support vector machine, right? Because if you recall, we have for each tag a classifier is saying that we train individually on the decision whether this particular shoe belongs to that tag or not. And this is basically how we train them. We have for each tag a set of various classifier problems, support vector machines, neural networks, etc., k-nearest neighbors, and then we let them train and run against each other in a cross-validation setup in order to come up with the best and most accurate classifier based basically on precision and a scaled recall in order to make the call on which classifier is the one for this particular tag. talking about the feature space, we use everything we get. It's, as I said earlier, it's total chaos, right? Amazon may provide you with totally different data in their product data feeds than Amazon, than eBay or Zalando. Basically, we take everything we can. We use a downscaled part of the image, basically 16 times 16 pixels in size, grayscale. We use as a different part of the feature vector the title plus the description. We're currently testing continuous word embeddings, but to be honest, bag of words still works better for us, which is basically one way of modeling your feature vector, which is very interesting. But from my experience, the simpler methods usually are more robust, and in a highly noised domain like that, simple is usually what wins. So talking about results at the end of, and coming to the end, it's unfortunately hard to see. I apologize. So basically, what we do is we look at not only at the precision and recall score, but at an F1 score that we weight by the popularity of the particular item. So the more people look at particular items, the more important it becomes, and the more it pays into the accuracy measure. Because we don't want to fix issues in our content that nobody looks at anyways. We want to make sure that the content that's actually been seen is accurate. And that's why we use what we call an average quality score, which is basically a modulated or scaled F1 score for our results. And we drive that across all countries. I skipped that earlier. We're in 14 countries. So the nice thing about it is we don't have to speak these languages in these countries, and among which are Poland, Spain, France, Italy, etc. And we usually gain above 92% in F1 score. So that's really, really cool. And that's been what we've been doing for the last 8 years. Right, that's it. Any questions? All right, there we go. How do we earn money? That's a very good question. How do we earn money? That's the question. So we are basically in an affiliate business. I skipped that out. That means that as soon as a user, let's say you're a user, right? And you're looking for a particular pair of shoes, and you find the product you love. Then you click on the product, and you get redirected to the online shop that actually sells the product. So there's two ways. The first one is we earn a commission based on your shopping cart value, or we get a CPC, a cost per click, which is basically a monetary value that we earn in the instance of the click out. So this is basically the business model. It's relatively common in the affiliate world, and we offer both. So CPO, or like commission-based, and click-based. All right.
Are all your tags mutually exclusive, or how do you deal with those which are not?
The question is whether all the tags are mutually exclusive or not. As a matter of fact, on the lower levels, they're not. So there is some overlap on the lower levels, such as you could have a skirt that's for summer, but that's also for your prom night, right? Or could have particular applications on it. So usually, the lower you get, the less distinct or the less unique the tags become. That's usually not a problem because at the point when the product reaches the level, we're basically disabling the mutually exclusiveness and just let the site, as soon as it classified decides, okay, I'm a summer skirt product, or the item that I'm currently looking at is a summer skirt product, you assign the item right away. Whereas we would mutually exclude basically all the others based on a confidence level on the more upper level. You could say, as a rule of thumb, if you go down to level 3, they're not mutually exclusive anymore. There were more questions. There we go. Come on. Do we have an API? Yes, we do have an API. As a matter of fact, I skipped over that because the slides were broken. We're 250 people. We are sitting next to the huge tower, basically Park Inn at Alexanderplatz. And so yeah, we have an API not only for native mobile apps, but also for enabling other businesses to attach themselves to our database and make use of the structured data that we get out of it. Yes, we do have an API. We have about 700,000 visitors per day. That's basically over all 14 countries. So Germany is by far the biggest, LadenZeile.de, which is our German brand. And you could say it's 50% LadenZeile and then the other 13 countries. So approximately that. Yeah, Jasper.
One question on your data. When you tackle external data, what's your experience with data like movement of users on your website? I can imagine it improves your precision of the results you're showing.
Yeah, that's a tough question. So the question is whether we are exploiting the data that we're gathering, the movement data, the journey data that we gather from our users, how they behave on our site, and whether we can benefit in the classification problem from that. As a matter of fact, we do to the degree that we know what people actually look at. Sometimes we do know, for example, that porn articles are clicked like crazy. Right? And if there is an unusual spike in clickouts, then it's often because it's either a wrong item, a misclassified item in a particular category, or it's of particular interest, right? So yes, we do use that, but the primary use case is for our tracking data to steer our marketing campaigns, right? However, in the space or problem space of classification, we only use the information directly, whether we are, what's the popularity of an item, what's the value of an item for us as a business, not so much in making the decision whether it's a shoe or not. Cool, there we go.
For unsupervised learning, you need clean data, right? So what is the effort or estimation for you approximately how much it costs to get this kind of clean data to learn to, of the overall cost of your machine learning?
So the question is about the costs of training, if I'm getting that right?
Not training itself, but getting the clean data, right? Because it's like labeling and labeling the classes. It sounds super expensive, right?
Yeah. Okay. Got it. So how do we train the system, right? Maybe let me elaborate on that a little bit. How do we train the system? As a matter of fact, the good thing is that let's imagine you get a summer skirt product that you as a human can classify right away as a summer skirt product. Then you would assign the tag summer skirt. And based on the taxonomy, you can exploit the hierarchy and go all the way up and reason your way up in the tree that you know if it's a summer skirt, it's definitely a skirt, right? And if it's a skirt, it's, you know, women wear skirts, right? So it's a women's product. Plus, it's definitely a fashion item. That also means it's not a furniture item. So by assigning one very specific tag, you can usually indirectly manually assign a lot of tags manually, and by that provide training data. Because what you need to understand is that we get a lot of unannotated data, and then we have about, let's say, 1 to 2% of the items manually assigned. We did that years ago. And have basically the information, what tags are assigned to these products, being fed into the training process of the individual classifiers. You know, talking about the costs, we don't do that anymore. What we do is basically, while cleaning up, that we generate additional value. But why isn't it expensive? Because as soon as you assign one very specific tag, you can reason multiple tag assignments all the way up the tree. So that's why generating training data is for us pretty cheap, to be fair. That's also cool because as soon as you look into deep learning methods, which interestingly don't work so well for us, you need a lot of training data. And we got a lot of training data, that's for sure. Because over the years, we've been correcting our categories, usually with a precision of about 90–95%. You still have 5% incorrectly classified items per tag. That generates a lot of food for the machine to learn. Yeah, so that we got a lot of training. I would say, like, of the 130 million products, I'd say we have 20 million training data accumulated over 8 years.
Unfortunately, it was really out of time.
All right? Okay.
It was really interesting, and you were, as I knew, you're probably one of the most prolific talkers, so I was really excited about the questions. Thank you so much.